Hi, this is Mr. Mel, and we're going to take a look at a quantitative circular motion problem. This problem is a little simpler than the next one we'll see. So we have a roller coaster here, and at the top of the loop we're moving at some speed. We can describe the curve at the top of this loop by defining a radius. And we're saying you're sitting in this car, you have some mass, 75 kilograms, and the question is, what kind of apparent weight are you experiencing? So that's the question. What we need to do next is draw a force diagram. And again, if you're in Dr. Holt's class, this little bit about the positive R isn't going to be something you're familiar with. You'll have to use whatever techniques you learn. So what we want to do here is define towards the center of the circle to be the positive R direction. And since we're sitting in this roller coaster seat, the surface is going to be exerting a force downwards on us because we're basically upside down, and our weight's obviously towards the center of the earth, in this case down. So both of those are pointing in the positive R directions. Now, what I didn't include here, which I should have, is a net force that's also pointing downwards. So the net force is a combination of these two forces, and the net force is providing a acceleration in the positive R direction, and that's what's redirecting us around the circle here at the top. Now this next part, remember that we have a little bit different notation for circular motion. Instead of talking about the X and Y components, we talk about the R and Z components. So as a little test to see how much you remember, you should pause the video here and try to write these two forces in component form, using this as the general form. So if you did it correctly, you should have arrived at these two things. Now this is a little tricky because look at this. This is a very unfamiliar result. You're writing mg in this first slot here, and it doesn't have a negative. You're typically used to going 0, negative mg without really thinking about it. But you have to realize that the gravitational force here is pointed in the positive R direction. So it's positive, and it goes in this first slot here for R components. So we take those two components, and then we use Newton's second law that says the force in any direction is equal to the mass times a component of the acceleration in that direction. And we simply substitute in, and we get a general formula here that we'll work from. Now we think about what the question asks. We say that, well, the question is asking for the apparent weight. What is the apparent weight? That's the normal force. So let's solve for that. And then we get here and we say, we have all these things, but what's the acceleration? I don't know. But I do know that the acceleration, the thing that's redirecting you around the curve, that's changing your velocity, is related to your current speed and the radius of curvature at that point. So I can make a substitution. And once I did that, I have all the values, and assuming you put it in your calculator correctly, given these values, you should get a value for the normal force of 2265 newtons, which is actually quite larger than the normal force you're used to experiencing, which would just be 75 times 9.8. The normal force you're used to experiencing is equal to your weight, so this is quite a bit larger than that. Alright, so hopefully that helped. Again, what I would say is do this problem on your own, a little bit close to the exam to make sure you understand it. Alright, thanks.